for next week. I have to sit down. It's going to have an Excel spreadsheet attached to it. I'm kind of excited about it. Got to find the time to do the damn thing. But your book, well, I don't know what your book calls it. I've seen this called something along the lines of the empirical rule or the 68, 95, 99, 100 rule. Maybe some of you have heard this before. So anyway, I'm going to call it the empirical rule just because I've seen that quite a bit. I'm going to tell you why they call it empirical. At least I think why they call it empirical. Sometimes it's also called the 68, 95, 99 rule. It's sometimes called other stuff and other things. But these are the two terms that I most frequently kind of see reference to. Whatever you use, you got to start with a big if. If you have what kind of data? How did you describe this data? More specific than that. What was the shape of our data? Bell-shaped. Yeah, raw data or grouped, as long as you have a graph of it and you look at that and go, that's bell-shaped. So if you have approximately bell-shaped data. So, Lloyd, yes, raw data for sure, group data for sure, but take a look at it. Look at the graph and say, okay, that's a bell shape. I can call that a bell. It won't be perfect. If anybody's sitting there going, how do I know if it's bell shaped enough? Anybody thinking about that right now? You don't have to be. Oh, good. Center's like, no, I'll worry about that later. Good, because there are ways to measure bellish enough-ish. There are ways, and we're going to learn some of those in here too, but right now, just look at it and go, okay, it's a bell. Good, good for you, good for you. So if you could say, yes, check, I have approximately bell-shaped data, this is totally rad. Number one, about 68% of the data will lie within the first standard deviation. Roughly 2 and 3 of the data points are going to land within that first standard deviation. We got about 67%. That's damn close. And it's going to happen with any bell curve. That's damn badass. That's a lot of swearing, I apologize. So, we came close. We got to see. That's why I said, I don't care if you guys include 31 or 0 or not. If you included it, maybe it's up to 70% or 71% or something like that. I can live with that. That's still really, really close to 68%. It's a small data set. That's where the quiz is going to help us out, because the quiz is going to have you guys using a simulator to run thousands and thousands of trials. So you'll be able to see what happens as it goes way above 35. So the fact that we got that close to only 35 makes me go, hell yeah, data. So, Kelly, about your confidence intervals, this is where it comes in. This, I'm going to put a little star next to it, because this one is what you will often see in research journals. You're going to get about 95% of the data within 2 standard deviations. We got 94. That's hella close. Like ridiculously close. Like, let's dance close, but we don't dance too much because we knew it was going to happen. Well, you did. That's kind of cool. You didn't know it was going to have to happen anyway. Once you get out to 3, now, hopefully you also understand why the percentage went up. All the data here is also here, plus more. Does that make sense? Mm-hmm. So you could subtract the two and say 95 minus 68 is 27%. Mm-hmm. That's the data that's outside of 1 but inside of 2. So over on this graph, it's like this data here and this data here. That's about 27% of the data. So roughly 1 in 4 of the data points is there. And you can do all kinds of fun geometry like that. You don't have to in this class if you don't want to. There's all kinds of fun denominations you can do. Once you go out to 3, you get almost all of it. I'm going to put about 100%. To a tenths, it's actually 99.7. To which some of you go, okay, who cares about the extra 0.3? Which is a good question. So what's the difference between 99.7 and 100? Well, 0.3%. Who cares? Okay, so I like to close the day with maybe an answer for who cares. So this really isn't 95, it's 95.45, if my math is done correctly in my head. This is not 68, it's 68.24, if my memory is serving me correctly. I'm not as sure about that one, I'm pretty sure about this one, 95.45. Who cares? Well, I think people that make like laptop computers care, people that make those little wireless TV things, those little cable-driven or wireless-driven TV things, cell phone manufacturers care, people that make little camera cards, SD cards, little mini SD cards, things like that, they care. Why do they care? Well, how many of those things are made in a given year? Millions? I think that's a pretty damn good explanation, John. Millions, right? So what's the difference between 99.7% of a million and 100% of a million?
A lot.
A chunk, huh? A couple 10,000s? Yeah?
Yeah.
So suppose that these standard deviations represented the workable lifespan of, say, an SD card for your camera. Workable lifespan, correct? And you're only doing your tolerance to 99.7%, which is 3 standard deviations. 3 standard deviations is enough, Rule told me. So you're saying it's good, it's good. So you're missing the other 0.3% of the millions. So you're missing a couple 10, 30, 40, 50,000 camera cards. Now of those 30, 40, 50,000 camera cards, roughly half of them are going to land on the awesome side of average. Like the ones that last a really long time, like way longer than they should. I still have a Walkman from 1986, it still works. Phenomenal, can't believe it. Should probably stop using it. But the other half of those 25,000, 30,000 are going to fall on the very short-lived camera card side, right? Which ones are going to get the reviews in Amazon.com? The bad ones, right? The bad ones are going to get the 1-star reviews. This piece of crap out of the box didn't work. What are people going to stop doing? Buying that card. What's going to happen to that company? Well, they can react to it and fix problems, or they can go out of business because they can't support the manufacturer anymore. So that's why 3 standard deviations isn't enough when you're making millions and millions of things. You guys ever heard of Six Sigma? This was a corporate thing that happened about 15, 20 years ago. 6 Sigma is like 6 standard deviations. Go out and measure for 6 standard deviations. Then you've got 99.99999. You're missing like 1 in a billion at that point, or 1 in 10 billion. So you can live with that person because that person is the one you contact personally and say, let me make your experience better. This is why the Lexus car manufacturer. You ever heard the story about Lexus? The car manufacturer. You now know that Lexus is like a high-end car. Well, I shouldn't say it's a high-end. It's a higher-end car, or it's got this association as like luxury. Lexus, it's got this name, and it's got this connotation. How did it get that way? Do you realize that one of the first things that happened to Lexus was they had a huge recall? They put their first batch of cars out. There was something wrong with the very first batch of cars they ever put out. You know how they dealt with it? They went to every person's house that had a recall, took their car away and delivered a paid-for rental for as long as it took them to fix the problem. Then brought the Lexus back to them. What did that do for company image? Oh boy, it's genius marketing. We got a brand new car and the first thing we release has a bug in it. Microsoft does this all the time, but we've just grown accustomed to it. Oh, it's Microsoft, we just got to deal with the crap and they'll send us an update. Apple, oh, it's buggy, they'll send us an update. No. If Apple acted like Lexus, whoever has replaced Steve Jobs would come to your house, hand you another iPhone, take your iPhone, deal with it, bring it back, probably with Chinese for dinner, and then say thank you and have a nice day, here's a bouquet of flowers and we'll see you next upgrade. That's where variability plays in, right? That's where this is important. This gives you an idea, not only of percentage, thank you, Anna, but also of quantity. How long, how much, how many, how few. Stuff's awesome. Stuff's totally awesome. It's powerful stuff. More on Tuesday, yes?
Yeah.
Yes! Thank you guys. Have a great weekend. Be well. We'll do the in-class quiz on Tuesday. We didn't quite get to it today. That's okay. We'll do it.
You've been saying that for like a week and a half.
I have. But that's because you guys keep taking me down these paths that I love. It's okay. There's no rush. We'll get to it. It's all part of building the picture. It's building the picture.
One more 89.
Yeah. Is this the histogram?
Yeah.
Yes, let's figure this out, because I don't remember this either. Okay. So if we go to your stack...
Can you turn this on?
If you don't mind, Candace, that'd be great.
I don't know
just
how.
close the screen, spin the screen around. That works too. Actually, that's the record.
Oh, sorry.
It's okay. No, just do this.